What we're going to be talking about today is UVM, what's now, which is where is the standard today, what have we been working on as a group, the members of the committee, as well as all of yourselves over the last few years, and then we're going to get into what's new, UVM 1.2, which is under development now and should be emerging pretty soon. Short agenda for the introduction. We'll talk about the working group history, what's brought us to this point today, how you can contribute to UVM, and a quick summary and some next steps. So the charter for the UVM working group is to define a standard technology and/or methods to realize modular, scalable, and reusable generic verification environment. I think many of you are probably using that environment today. We formed in February of 2008. The co-chairs, Helen Miller from Freescale, Tom Alsop from Intel. I serve as secretary. Background, the IEEE 1800 system Verilog lacked some VIP interoperability standard. Great language construction, but the interpretation of building methodology was left up to you. And there were several that started in these earlier days of system Verilog. This committee formed to create interoperability among some of those, and then eventually to create this unified standard. And the goal was to create a standard that allowed you all to share verification IP, lowering the cost of verification and generating interoperability throughout the industry. Some milestones. Back in 2008 is when we got started as a working group. The recommended practices of interoperability among OVM and VMM was the first standard created by this group. And the standards are there at the top. We then set about creating the UVM 1.0 standard. We brought that out first as an early adopter version, and then about a year later, the 1.0 library was standardized. After 1.0, we quickly brought out a 1.1, which added the register layer. That was the biggest major component of the 1.1. And then we built a set of updates, UVM 1.1A through D, with minor changes, mostly bug fixes reported through our members to improve the quality and a bit of usability around UVM. The work we're doing right now, up there in the gray color, is the 1.2. So there are some new features. When we bring out a new library, we need to update the standard if the APIs have changed. And that's what drives the 1.1, 1.2 numbering. A through D, there's no change in the APIs, so those are just library updates. So 1.1 reference, and that's the way most of you will work with this working group, is to use the reference implementation. It's in very widespread use. We commonly talk about the library as UVM, but really as a standards organization, it's the language reference, the reference manual that defines UVM. The reference library is an implementation of that standard. It defines the features that fulfill the charter of the group, including component definition, factory, messaging, register layer, and more. These are the elements that you use in the library, and we'll be talking about those in the tutorial today. It enables verification IP to scale from block to system, and it has been validated on multiple simulators. And that's, I think, what's helping to drive a lot of the interoperability you all enjoy with it. It's been broadly adopted through the industry. The LinkedIn community of 4,300 members was when I created this slide, and we're about 4,400 members now. We keep increasing the size of this community. More and more folks continue to join with you all in using UVM. LinkedIn membership has passed OVM as of April last year. So by all intents, this is the methodology that the bulk of the industry is using for verification today. There's an active community. I can't say enough about how the community, the standard, and you all together form this triad that makes the standards work. So the community is filled with folks that are members of Accellera, non-members of Accellera, industry experts, and what we're finding is that the forums are very active. We continue to have multiple posts each week. Each thread itself has responses. You have access to experts like the ones who'll present today, the ones who are in the room as well, and the ones that you don't even see because the community is so large. There are links to technical material, tutorials from Accellera. There's a special forum for commercial materials, so the different vendors EDA vendors, IP vendors, tools vendors. We're all providing links to some of our own content there as well, so that you can see what's available in the standard and what's available in the commercial community. These are the things that make the standard vibrant. Contributing, you need to be an employee of an Accellera member company in order to actually contribute to the standard, that is to work on the standard's development, to edit the library, things like this. So if your company is a member, then we welcome you to work with us in the UVM working group. If your company isn't a member, you may want to encourage them to join. But everyone everywhere can use UVM. So you can download the standard. It is obviously open source, Apache licensed, open for you to use. UVM World forums, now housed on accellera.org, are open as well. You do need to register to post a question, but that's all you need to do, and you can have your questions answered. You don't need to register to read the forums, of course. You can contribute code examples, tips, and more into the uploads area, and you'll find a number of interesting pieces of content there as well. And you can report Mantis items or errors. So you can do that through the forums, and we're welcome to take issues that you found with the library that need an update, issues with the standard that need an update, or even new ideas. So we're welcome to all of that. So the summary, next steps, UVM is a well-established industry standard. We've had this tutorial here for 3 years now, I believe, and each year we have a filled room. And we really appreciate that. It's a great group that you all are that contribute to the standard by using it. Contribute your knowledge, contribute your experience. And from the working group, it's a way for us to really feel very good about the work we do. So really appreciate your contributions. There's an active support community, as we said, through the forums. Very good way for you to get your questions answered and actually find new material, new resources. And it's a living standard. So we continue to evolve UVM, adding new technology to it, making it easier to use, and the UVM 1.2 will continue in that effort.
So this is a tutorial. We're going to try and teach you a few things about UVM. So typically it takes us 3 or 4 days to teach UVM, and that's a pretty intensive training class. And we're going to try and cover some of that ground in just 3 hours here today. My role here is really just to lay the paving slabs, to lay a good foundation for the other guys to build on. So I'm going to take you through a few of the basics of the UVM class library. Let's start off with basic what's and whys, what it is, what's it all for. Then look at some highlights of UVM, look at the big picture, then dive into execution phases, the agent architecture, and then talk you through an example. The code from the example is still kicking around on the Doulos website if you want to go download it at some point. So what is UVM? It's the Universal Verification Methodology. That's what it stands for. Practically, it's a system Verilog class library. UVM has always had aspirations to be mixed language or multi-language, and indeed, in a sense, it is. But the implementation that you download is system Verilog. It exists to do constrained random coverage-driven verification, and as Adam emphasized, it is a standard. It really is a standard. People still ask me, what on earth should I be using UVM for? What's wrong with OVM anyway? Well, UVM is the standard, and the reason you should be interested in UVM if you're starting out right now with constrained random verification is that it's the standard that enjoys the broadest adoption amongst the users and from tool vendors as well. So why UVM? Well, I'm going to keep this very simple, just 2 points. Point number 1, you should be using UVM because it will help you to adopt best practice. It'll help you to create code that's consistent, uniform, avoid you having to reinvent the wheel, avoid pitfalls. And then secondly, for reuse. If you're using UVM, it's because you want to be able to reuse something. UVM enables you to reuse verification IP, verification components, verification environments, tests, people, know-how. So reuse at a technical level and reuse at an organizational level comes from UVM. And as we go through today, the reason why most of the things that you're going to see are the way they are is to enable reuse. That's what it's really all about. If you don't understand that you're here for the sake of reusing stuff, whether it's code or people or tests or whatever it is, you've kind of missed the point. And frankly, you don't need UVM to write test benches. You can write your test benches in Verilog or C or VHDL or C++ or whatever it is. UVM specifically gives us reuse. So some highlights. This is a quick laundry list of features. In UVM, we separate tests from test benches. We use transaction level modeling for communication. We use the factory and configuration as two specific mechanisms to aid with reuse. We use sequences for generating those constrained random stimulus. We use objections as an end of test mechanism, a way of ending the test, as a standard collection of message reporting features, and a register layer. So you'll see allusions to these points throughout the tutorial today, and I'm going to try and show you how some of these parts fit together just to get you started. So let's start off by talking about tests versus test benches. So down at the bottom, we've got a design under test, then we build our test bench or reusable verification environment. And the idea is that this is a body of UVM code, system Verilog code, that's created once, and then apart from the odd tweak and bug fix, largely left alone, and may well be created by verification specialists. So many organizations these days separate verification specialists who are good at stuff like UVM and writing clever test benches from application experts who write tests. And you don't have to organize your organization this way to use UVM, but a lot of companies using UVM do this. So the reusable verification is a body of code written using the UVM class library that's relatively stable, created near the beginning of the project, lasts throughout the project, and then gets reused, if you like, across multiple tests. So some organizations will have those same people writing tests, some organizations will have different people writing the tests. And each test reaches in and tweaks the reusable verification environment in some way. So the tests are typically small pieces of code. The tests reach into this verification environment and just tweak it, mess around with it a little bit, without actually changing the code itself. And this is right at the heart of what UVM is all about. As I said, it's all about reuse. So what we're doing here is reusing a large body of code, the verification environment, having that code do different things, but not actually changing the source code. And we're using a couple of mechanisms, the configuration mechanism and the factory mechanism that we'll refer to throughout this tutorial to do those things. So those mechanisms allow for unanticipated changes so that you can take your verification environment and use it to do clever things that nobody had thought of when the environment was first created. Now let me talk you through the big picture of what a UVM environment looks like. This really is UVM 101. This is how you should picture a UVM environment, a UVM test bench. Down at the bottom, we've got the design under test. Then comes the verification environment. So in UVM itself, you see this word UVM env, env being short for environment. That's a particular class in the library that represents verification environments, or test benches, if you will. At the bottom, we've got our design under test, the chip we're interested in testing. And you'll recognize that chips these days have a whole bunch of interfaces, network interfaces, bus interfaces, serial interfaces. And what we're going to do within our UVM environment is to create an agent, a UVM agent, one of the reusable verification components, one agent for each interface on the design under test. And the agent itself has a standard structure. An agent consists of a sequencer, a driver, and a monitor. We'll see sequencers, drivers, and monitors referred to a lot throughout the next 3 hours. So a sequencer is going to generate stimulus, generate test stimulus. A driver is going to convert that test stimulus into pin wiggles and stimulate the pins on the design under test. A monitor is going to look at those pin wiggles, interpret those pin wiggles, build up transactions, and send those transactions off to the rest of the verification environment for analysis. So that's the basic picture, with one of those agents for each of the main interfaces on your design under test. So what you'll do in practice is to start constructing a verification environment, identify all of your interfaces, try to find agents for each of your interfaces, and if you're lucky, somebody will already have created an agent for you, or you go shopping on the internet to try and buy an agent for that particular interface, or maybe you write one from scratch. Well, perhaps you go surfing on the web and you find somebody in some remote corner of the world who's selling you an agent for your particular interface. You bring it in, you get all this agent in-house, which is just a bunch of source code. Maybe it's compiled. You do not want to start hacking that source code, right? And you don't have to. You don't have to start hacking that source code because we can bring in the two mechanisms of the configuration database and the factory. And at this stage in the game, those two things are just bits of jargon. But what they allow us to do is to reuse this agent and change it, make it do different things, change its structure, change its behavior, change its functionality, without having to hack the source code of the agent. So right at this early stage, you can see reuse is key to all of this. We're being able to reuse this verification component without having to go in and hack the source code, using the configuration database and the factory mechanism. Then we go ahead and we instantiate an agent for each of the major interfaces on the design under test. We may then optionally make use of the register layer. And the register layer, which Tom is going to tell you all about later on, is a way of abstracting the registers in the design under test so that you don't have to build physical addresses into your test. Instead, you can just access registers by name. So we can be reading and writing agents buried deep down inside our design under test without having to know the actual address in terms of the memory map of those particular registers, without knowing what protocol we're using to access the design under test, without knowing the endianness of the interface. All of that stuff can be abstracted away. Then we build other reusable components in our verification environment that are going to consolidate and coordinate the behavior of multiple interfaces. So we have virtual sequences. Virtual sequences sit at the top of the pyramid of stimulus generation. So virtual sequences are going to control and coordinate lower level sequences that are generating stimulus. And we have scoreboards. Scoreboards are typically a way of consolidating output from multiple agents and doing checking and coverage collection, those good things from constrained random verification. So in the box on the left, UVM env is a verification environment that's going to remain relatively stable, and we're going to reuse it as we write multiple tests. So you or your test writers will create multiple tests. The tests will then use the same mechanisms that I called out, the factory and the configuration database, in order to customize and tweak the verification environment to suit the purposes of a specific test. And ultimately, under the hood, that's all using the magic of object-oriented programming. UVM is using fancy object-oriented programming techniques in order to customize and tweak the behavior of the verification environment. But you don't have to know all the details. UVM has wrapped those techniques up for you in a number of ways, including the factory and the configuration database. I won't say that you don't have to become an object-oriented programming expert, because I know from many, many years of trying to teach this stuff that engineers like knowing what they're doing, right? You don't like it when we say, you don't have to know what you're doing, just push these buttons. No. Engineers have to know what they're doing. And so you are going to need to learn a fair amount about how to write good code, how to adopt good coding style. You're going to want to know something about what's going on under the hood, because we just like that. But nonetheless, UVM encapsulates a lot of these things and makes them easier to use. Now let's start getting a little bit closer to the source code. So UVM is going to distinguish between components on the one hand and transactions and sequences on the other hand. So on the left-hand side of the slide, we've got components which are structural. the structural organization of the verification environment, what it's made of. Components like agents and sequencers and scoreboards and coverage collectors and all of those things. They are quasi-static, by which I mean they get created right at the beginning of simulation. So actually, this is all system Verilog. It's all class-based system Verilog. All the code that you're going to see here is made up of system Verilog classes. And it turns out that in system Verilog, classes are dynamic. Instances of classes get created at runtime. So all of this stuff is actually created at runtime during simulation. But we have to distinguish between things that are created at runtime at time zero, right at the beginning, and everything else, stuff that's changing over time. So UVM components, which are quasi-static, are actually created at runtime during simulation at time zero. Time zero has a special significance. And that's when the structure of the UVM environment gets created. And then simulation runs as you know and love it. Time passes, events happen, non-blocking assignments get executed, all that good system Verilog stuff. And over time, we create other kinds of objects to represent sequences and transactions. And those are the guys over on the right that are dynamic. So in the bottom half of the slide, we can see some UVM code, some classes. We'll see two major types of class. On the left, we've got a component. So class myComp extends UVM component. That's quasi-static. It's going to get instantiated at time zero. On the right, we've got a sequence item that represents part of the stack of generating some stimulus. And that's dynamic. That's going to be created on the fly at runtime. And most of the fragments of code that you're going to see presented this morning are going to fit into one of those two categories. You'll see lots of classes. Some of them are going to be instantiated at time zero. They're quasi-static. Others are instantiated as time passes. So to structure what happens as time passes, UVM defines a bunch of execution phases. You'll see phases popping up again and again throughout the morning as well. So it all starts with the build phase. The build phase is the first of UVM's phases. What the phases do is to just structure the simulation from beginning to end over time. So we're going to divide up our whole simulation into a series of phases. During the build phase, all of the components get created. So on the right-hand side, we've got a nested hierarchical structure. Each of the boxes in that hierarchical structure is an object, which in object-oriented programming parlance is an instance of a class. So this is all fancy object-oriented programming. But you can think of each of those boxes as a component, like a module in Verilog. It's not literally a module. It's an object. It's an instance of a class. But it's playing the same role as a module. So it's creating a hierarchical structure. And then connecting together those components, connecting up the hierarchical structure, we've got these dark blue blobs, the circles and the squares. And these dark blue blobs are transaction-level connections, known as ports and exports. And this terminology of ports and exports actually got inherited from System C. So UVM gets its transaction-level jargon and some of the rules and regulations from System C. So the communication amongst the components of the verification environment is going to be transaction-level, which many of you will have some idea of what that means already. So after the build phase comes the connect phase, and in the connect phase we join everything together. And the idea, of course, is that we're going to start off by running the build phase for all of our components, and when the build phase is entirely complete, then we move on to the connect phase and connect stuff up, connect all of these components together. Then we've got a couple of housekeeping phases, end of elaboration, start of simulation, when you can check stuff, open and close files, print out diagnostic messages, whatever you like. And then we go into simulation proper, where time passes and events happen, and that's the run phase. So you can see the picture on the right has sprung into life, and we've got these yellow transactions being generated and passing between components. The run phase is further subdivided into 12 predefined subphases, broken down into 4 groups of 3, reset, configure, main, and shutdown. So these are built-in runtime phases, and they're a built-in way of structuring what happens during simulation. So initially we're going to have a reset phase where we run all the verification activity associated with resetting the various parts of our design under test. Then we configure the design under test. Then we do the main part of the test, and then a shutdown phase at the end. Then we move on to a bunch of housekeeping phases that we're going to run at the end of what you normally think of as simulation. Okay, that was the execution phases. Let's start diving down into some source code and see what that's going to look like. So here we've got some fragments of code. This is what UVM code looks like. The parts in red are actually names that are built into the UVM class library. The parts in black are user-defined. So here we've got a component that we've created by extending a UVM agent. So the UVM agent is that structure containing sequencer driver monitor. Then we represent the build phase within our component by this function void build phase. That's just a fancy function. It's embedded inside our class. And what it does, if you remember, the build phase instantiates components. So inside our build phase function, we've got some calls to another function, create, that are going to instantiate the various components inside the agent, the driver, the sequencer, and the monitor. And those are known as factory method calls. What we're doing here is instantiating components. So if you're familiar with object-oriented programming at all, we're calling the constructors of objects to make them. If you're familiar with Verilog, it's like instantiating modules. We're just instantiating, bringing into being lower-level components. And we're doing that with this mysterious magic spell, my driver, : type ID, : create, the bit highlighted in red there. That's a factory method call. You don't have to understand it. You just have to believe me that it's a good thing. What it does is that it enables somebody else to come along later and tweak your code without touching it, without actually having access to the source code and without going in with a text editor. So that's one of the key values of UVM, that you can take existing IP, existing code, change what it does, change the structures you're creating without going in with a text editor and editing the original code. And that's what these factory methods do for you. Then we move on to the connect phase. So the connect phase just looks like another function that you write in your user-defined components. So this connect phase is connecting up a sequence item port on the driver to a sequence item export on a sequencer. It's just like a port connection list in Verilog, only it's all written in fancy object-oriented programming stuff. So we're taking our port on the driver and just connecting it up to an export on the sequencer, establishing a connection so the two things can talk to each other. So big box at the top here is a bit of verification IP, or some part of it. Imagine this was written at some stage by somebody on the other side of the globe. They created an agent to represent some protocol, wrote all of this code, packaged it all up for sale, stuck it onto the internet, and you went out shopping and bought this code. So you've downloaded it, you've now got this agent and you want to use it for testing your design under test. Only when you look at it, you decide you don't want it to do exactly that. You want it to do something slightly different. What are you going to do about it? Well, that's where you may be thinking factory. So the factory mechanism is going to allow us, if we wish, to change or replace or override some aspect of this existing code. So just to give you a flavour, down at the bottom here, we've got a type override that's going to work with the factory. So you can think of the factory as being, well, a factory, something that makes something. And in UVM, factories make objects. So by default, if we take the line my driver equals type ID create, that's going to create an object of class my driver. We're asking the factory to create a driver. And the guy who originally wrote this code thousands of miles ago and many months ago just said create something of type my driver. Now we can have this very function call create something different by setting a type override. So the bottom line on the slide here, my driver, type ID, set type override, blah, 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 is saying, no, don't create my driver, create alt driver instead. And the power and the beauty and the significance of all of this is that you can come along and change the behavior of some code that was written by somebody else who you're never going to meet months ago on the other side of the world. You don't need to go in and actually edit and hack their code. You can leave their code exactly as it is, write a new piece of code that will be part of your test, and say, for the purposes of this particular test, let's go in and replace one driver with another driver. There's a lot more fine detail to that to learn, but that's the basic idea of what's going on. So let's pop back up to the top level again and revisit what's going on. So we've got a design under test. We've got a verification environment, think test bench. We've got a number of tests, which you may be writing yourself, or you may get application experts to write in your organization. Each test is going to use typically the factory, the configuration mechanism, and some other techniques as well, to reach in and tweak the behavior of the verification environment to have it do something different. And in the verification environment, we're going to have one agent for each of the interfaces on the design under test. That's the big picture in UVM. That's the thing to keep in your head. And each agent will consist of a sequencer that runs sequences. The sequence runs on the sequencer. The sequencer is quasi-static. It's a component. It's connected to other components. Think Verilog module instance. The sequence is dynamic. It's generating some stimulus. It's running over time. So everything here is quasi-static, created during the build phase, right? Connected up during the connect phase. Then during the run phase, things happen, time passes, our sequence runs, the sequence generates transactions. So a sequence runs on a sequencer, generates transactions, sends them to the driver. The driver wiggles pins on our design under test. The monitor looks at all those pin wiggles on the design under test, assembles the pin wiggles back into the transaction again, sends those transactions back off to the rest of the verification environment for doing analysis. So we have here the main elements of constrained random coverage-driven verification. The random stimulus generation is done by sequences. Sequences run on sequencers. They're often started from tests, even by virtual sequences. The monitor assembles our pin wiggles into transactions. We're using transaction level communication between all of these components here. Sends those transactions off into the rest of the verification environment that's going to do checking and coverage collection. Checking to make sure that our DUT is functionally correct. Coverage collection to check that we've done enough simulation. Of course, sequences and sequencers cause endless confusion, particularly for newbies, because what's the difference between a sequence and a sequencer? I've just realized I can say this in pirate speak. The difference is R. So the sequence and sequencer just differs by one letter, R, and that is so annoying. Who would think of creating two very significant names central to UVM and they just differ by the letter R? So a sequencer is a component. It's created at time zero, quasi-statically. A sequence is dynamic. It's going to generate some stimulus. Very different kinds of animals, and the sequence runs on the sequencer. So you've just got to be very sensitive to whether you're talking about a sequence or a sequencer whenever you look at some UVM code. Let's look at communication in a bit more detail then. Same kind of scenario, slightly different picture. If you're familiar with System Verilog, you know System Verilog has interfaces. Interfaces are bundles of wires. So connected to our design under test, we've got an interface which is going to encapsulate the pin level interface to the design under test, a bundle of wires. Up in our class-based verification environment, the UVM verification environment, we'll have a so-called virtual interface that points off to the actual interface. A virtual interface, well, I think of it as being a kind of fancy variable, really. A virtual interface is like a reference to an actual interface. So in your class-based verification environment, you have this reference to the actual interface. And so that's how, from the UVM world, we're going to get a hook into those pins connected to the design under test. We then connect the sequencer to the driver, using a TLM connection, a transaction level modeling connection. We actually connect a port on the driver to an export on the sequencer. We won't worry about any more than that, except to say that the driver is going to pull down transactions from the sequencer. So our sequence runs on our sequencer, the driver calls get or get next item or try get, and tries to pull down transactions from the sequence that's running on the sequencer. So we're using transaction level communication within the verification environment. We've got a virtual interface pointing off to the actual pins connected to the design under test. And then if we want to configure all of this stuff, if we want to parameterize or set different options in the normal sense of configuration, we do that through yet another mechanism that I referred to earlier, the configuration database. So I mentioned the configuration database and the factory as two very, very important mechanisms for enabling reuse. So the factory enables you to replace one thing with something else. The configuration database is just a fancy way of parameterizing stuff. So configuration database is analogous to parameters in Verilog or generics in VHDL, if there's any VHDL speakers out there. So it's all fancy and object-oriented and wrapped up in some mysterious jargon, but really all we're doing is parameterizing our verification environment. So just as you can parameterize modules in Verilog, you can parameterize the verification environment using the configuration database. So all of our components, sequences, can be pulling parameters out of the configuration database, and those parameters were set into the configuration database from higher up in the hierarchy. So those are the main foundations that we're all going to build on this morning. I'm going to finish my section, not just yet, but over the next few minutes, I'm going to finish it by talking through a Hello World source code example. This is a kind of artificial example because it's very difficult to do something very real in UVM that fits on one slide in a few lines of code, but it shows the main elements we've been looking at today. So we're going to have an interface. The interface is going to contain all of the pins that are using to connect to a particular interface on the design under test. So stuff like clocks and resets, address and data, blah, blah, blah. Then we'll have the design under test itself. And this is just a Hello World example. It's not real. So all we're going to do is to have our design under test print out a message like Hello World to say, yes, I've just received some stimulus. So here inside module.dt, we're importing the contents of our UVM package. UVM_PKG contains all the UVM built-in classes. And then in a Verilog always block, we're waiting for a clock edge, and then just writing out a message using UVM's standard message reporting facilities. So UVM info is a good, friendly UVM macro we can just use to print out an information message. So here, every time the DUT receives a transaction on a clock edge, it's printing out a message to say what I've received in the spirit of the Hello World program. Then we have the top level module. So in our top level module, in the module-based world, by the way, everything on the left-hand side of the slide is module-based. Everything on the right-hand side is class-based. So one of the themes, again, you'll see running through today is that System Verilog has modules, System Verilog has classes, UVM is a class library, so everything you're going to see that's UVM-like is going to be in classes. But we also need a module, lots of modules. So here we've got a top-level module. The top-level module is instantiating our interface, instantiating our design under test, and then has a System Verilog procedure, an initial block, that calls run test at the bottom. And run test launches the entire UVM world. It makes all those magic things happen in UVM. But before it does that, it's setting an entry into the configuration database. It's parameterizing the UVM verification environment. So we've got a call UVM config DB set. You'll see other references to UVM config DB later on. When you see UVM config DB, just think parameterization. All we're doing here is setting a parameter. So this is like doing a parameter override in Verilog or a generic map in VHDL. It's setting parameters that can then be used to parameterize and customize what's going on lower down, this time in our class-based verification environment. Then flipping over to the right-hand side, we've got a bunch of classes. So here we've got the agent, typical building block of our UVM code. So we have a class that extends UVM agent. It's instantiating sequencer, driver, and monitor through the factory in the build phase method. It's synchronized with everything else that's going on using the phase methods, and it's calling create, the factory method call, so that we can change our minds later. We can actually have this agent instantiate other components. Then the connect phase is connecting stuff together. Then moving up in our component hierarchy, here we've got another user-defined component, my env, that represents the verification environment. Phase methods again. In this case, the env is instantiating the agent. So just to drill this in, we have an agent, standard kind of structure for a class, multiple phase methods that are building and connecting together the hierarchy. Yet another component, the env, that has the same overall structure, you'll see this again and again, instantiates the agent. And then the test, which has the same structure again. So class myTest extends UVM test, the built-in class. Standard phase methods, so in the build phase, we instantiate the env. And then in the run phase task, which is a task because it's the one of the standard phase methods that's going to consume time, in our run phase task, we're going to complete this little hello world program in UVM by consuming some time and printing out hello world. So again, we're using the standard message reporting that you'll see referred to again and again, UVM info. That's just the standard way of printing out a message so we can get our hello world message printed out. We're also consuming some time to make this vaguely realistic with a #10 or #10 that's consuming some time. So our test here is taking 10 time units to run. So to actually get our test to take 10 time units to run, we have to start worrying about the end of test, the other highlight that I called out earlier on. So in UVM, the end of test is managed using objections. So the very first thing we do is to raise an objection. And when you raise an objection, you'll hear various talk of objections this morning. An objection is just saying, don't stop, I haven't finished yet. So an objection is an objection to the test ending. So our test component is saying, don't stop, I'm busy. Then it consumes some time and prints out hello world. And then when it's finished, it drops the objection again. And at that point, having dropped the objection, then the phase is over, the test is over, our hello world program is completed. So just to finish, remember as we go through the rest of the day, UVM is all about best practice and reuse. That's why we're doing it all.
Today I'm going to talk about the stimulus generation, the part of UVM that's very exciting. We're going to talk about sequence items, we're going to talk about sequences, we're going to talk about the tests that we use in UVM. It's a very large topic. We could literally talk all day about all the different kinds of things, all this different sorts of stimulus. We have many different needs, and so there's not just one right answer. There's a lot of different approaches that are taken with this, and some of it's controversial. Different people have very strong opinions about different things, but we're just going to try to present sort of a balanced overview about most of what you'll need to know to make those decisions yourself for what you need to do. I think in John's presentation, we sort of looked at a little piece of a test bench, and this picture of a test bench hasn't really changed in a very long time. When I started making test benches a great many years ago, we drew boxes and connected them with arrows. There's always been boxes and arrows. And if we were writing this sort of thing 15, 20 years ago in just straight ahead Verilog, the big fat arrows down at the bottom would be method calls. They would be task calls. This driver would be called a BFM, and it would have an API that had a, I want to do a write method, or I want to do a read method. And then somewhere else in my test bench code, I would have an address, and I'd have data, and I could make that call to do a write. I would put that in my call to bfm.write, and I would make that call. I'd also have other methods laying around for doing things like printing the transaction And the print method would have the same kind of arguments a read and write method would have. I would have a method for printing. In object-oriented programming, we sort of make a small change. The address and the data for a transaction always belong together. So what we do is we just put them inside a user-defined data type, a class. We group them together inside there. Everything that's related to the transaction can get put inside one of these data types. The second thing that we can do is we can put the methods that operate on that data inside this data type. So I don't ask something else to print my transaction. I ask my transaction to print itself. And that seems like a 50-50 sort of choice, but it's really not. Because transactions know how to print themselves. If there's a problem with printing transactions, I don't have to look around. Debugging gets easier because the things that operate on transactions are local. So what travels across that big fat arrow now is not a method call. Like in John's presentation, it's little squares. It's little transactions. It's instances of transaction items. It's objects. So sequence item, as John mentioned, is sort of the root class that we use for stimulus in UVM, a sequence item. And you can see here that for a bus transaction, I can group together the properties of that transaction, the address, the data, as well as metadata information, things that aren't really visible on the bus, like the length, perhaps. And a transaction type. I can say if this is a read transaction or a write transaction. And once I've created this box, this user-defined data type that contains and relates together all these properties, I can put things like constraints that will connect these different properties. So here I have a constraint that simply says the length is not going to be too big. The payload is never more than 255. And then I need those methods for the kind of things you want to do in your test bench with transactions. I want to print that occasionally. I just found a transaction. I need transaction, print yourself. I need comparison. Does this transaction that my monitor sent match what I was given from the other side? I need methods for comparing. And other utility methods like pack me all the values in this transaction together into a byte stream. There's a library of methods that's defined for sequence items in the UVM. I can build those methods manually myself, or I can use macros to do that. So you'll remember the UVM object utils macro from John's that essentially tells the factory about this data type, because later in my test I may want to change the kinds of transactions that are generated without touching the transaction class that's now built and working. And then I can put inside this macro some other macros that are going to expand to build a compare method, a print method, this type of thing. Utility methods that are quite useful. And that's how I'm going to capture much of the transaction-based stimulus in my test. But I don't just want individual bus transactions. What I really want to do is a write followed by a read. Or I want to configure all my registers. I want to send sequences. I want to generate a stream of these sequence items. I want to create a UVM sequence. The sequence itself is a sequence item, but it contains a method that will procedurally describe how we're going to create that stimulus. We don't want to lose sight of what we're doing. We're working on a constrained random verification effort. We can generate, using this kind of stimulus, very powerful, very flexible. It's fun and very cool. You can make your test bench do amazing things, but you need to be always guided by what is it you're trying to do. We have a verification plan that captures with coverage what it is that we want to see happen, and then we constrain our sequences to go after those coverage goals. The sequences themselves are objects. They're sequence items. They are data themselves. They're dynamic. They're going to be created. They're going to run their body method that will generate stimulus. And that method will create a stream of sequence items. It's going to go off to our driver and into the DUT. So the picture relates our sequencer to sequences. The sequencer has handles to 0 or more running sequences. And the sequences themselves have a method that produces sequence items. The sequence items go through the TLM port into the driver. When one goes, the sequencer asks one of the sequences for some more, and so on, until everybody's finished. So an example sequence, what does it look like inside? Well, the first thing to note is that sequences are typed, or they may be typed here. It's a template class, so my sequence is flavored with bus transaction. So I'm creating a bus read-write sequence here. And it contains this body method. The kind of things I'll do in the body method, well, I may want to do different things. So I can put what we call knobs, or what many people call knobs, to allow me to customize the sequence. So here, my body method, before it does anything, it asks the configuration database, tell me how many transactions I should generate. So he just goes in the configuration database, and he asks for the sequence length, for example. And then we have a repeat loop that says, okay, well, I'll go through this next loop that many times. Here's where I want to build and send transactions. So the first thing I can do is create a transaction, create a sequence item, create a bus transaction. Built into the UVM sequence is a request handle of type bus transaction. And then I can start that item. What the start item method really does is ask the sequencer, is it my turn to go? So if there's many sequences running in parallel, what start item does is block until the sequencer says, I want a transaction from you. Then when I'm ready to go, at this moment in time, I can get my transaction organized, perhaps just randomize it, and then I can finish it. And what the finish method does is really just give the sequence item, the request, give it to the sequencer, and then the sequencer is going to pass it on to the driver or what have you, and it's going to wait for that transaction to be finished. We could also write that sequence using the built-in macros, or we could write a slightly different sequence, actually. A different body method, I might begin by querying the configuration database, and then I have a macro here, UVM do with. The UVM do with will create the request, will randomize that request, and then give it to the sequencer, and then wait for the transaction to finish. The with part means I want to add a constraint. Here, my request type will be write. So that one macro line creates a request object, randomizes it, adding a constraint that it's a write, and then sends it to the sequencer. Once the write is finished, the next line there just pulls the random address that was used, and then I have another UVM do with that provides that address. So now I'm randomizing, choosing a read to the address that I just wrote to. So the macros hide some of this start item, finish item. There's a number of these macros. The UVM do is sort of the most basic, just build, randomize, and send a transaction. UVM do with is adding a constraint. Do on allows me to name a different sequencer. So I can, in my sequence, talk about other sequencers. And then sequences all run with a default priority, but I can modify that priority so that when the sequencer looks through the sequences that are running and chooses the highest priority. There's other macros for simply just creating, as you saw on the first slide there, just creating a request and just sending it. So I can just create, do whatever I want to my transaction to get it ready, and then send it. And in fact, if you look in the UVM do macros, there's UVM create and send macros. And if you look inside those macros, you'll see at the root bottom is the start and the finish item, like we saw before. So using these macros is totally optional. Sequencers are components. They exist in the component hierarchy of the test bench. They're part of the logical hierarchy of components that make up our test bench. The sequencer itself picks from sequences that are available and runs them. Calls the start method, which calls that body method we saw. The sequencers themselves are also templated. They're template classes. So I can build a sequencer that deals with bus transactions. And what that really is that's typing the port that connects to the driver. That port will be built to accept bus transactions or subclasses of bus transactions. And that's often how we use it, because we don't usually need to monkey around with the internals of the sequencer. The sequencer is going to send the sequence items to the driver via the TLM export, and responses can come back as well. I can subclass my sequence as well. I can create a my sequencer that's different from a bus transaction UVM sequencer, and I can add things. I could add handles to other sequencers. I can add information about the local environment that this sequencer is in. For example, some kind of configuration information. When I build multiple sequencers, they may be on different sorts of flavors of areas of the test bench. So I can capture that, and the sequences can ask the sequencer for that information. The alternative is to get it out of the configuration database in your sequence. Whether you use the top blue or the bottom blue box, it's up to you to decide for your particular situation. A virtual sequence, we call it a virtual sequence because it does not have that connection to the driver. It's typically just used at a higher level of abstraction within the test bench to talk to other sequencers. Each of the agents from John's picture has a sequencer in it. I need something to have those agents cooperate. I want to create collisions. I want to create interesting scenarios, and I need to orchestrate the behavior of different agents to get there. So I need to somehow have another layer of my test bench, another hierarchy logically for my stimulus generation. And I can get that through a virtual sequence. We see an example here in the blue box where in my sequence I have a handle to two other sequencers, two other master sequencers within agents, presumably. And I have a bus transaction sequence. I want both masters to go at the same time and generate traffic to the same address. So in the body method, I could simply fork off two sequences, sequence 0 and sequence 1, on master sequencer 0 and master sequencer 1 in parallel, using the same address. The point of the virtual sequence is to understand that it creates another layer, have the lowest level of sequencers cooperate. I'm building and running subsequences. I've created another layer. We can start sequences a number of different ways. A very straightforward way is look in my test. I want to create a sequence, my stimulus sequence there within my test, its main phase. I can create the stimulus sequence using the mechanism John talked about. I ask the factory, please give me my stimulus sequence. And then I can tell the sequence what phase it's running in. We'll talk about that in a moment. And then I can simply start that sequence on a particular sequencer. I'm calling the start method of the sequence. I say, sequence, start yourself on this sequencer. The start method gets called, which calls the body method, which generates the stimulus. As you saw in the previous slide, I can start sequences from within sequences to create that layer. There are macros for this, or because a sequence is a sequence item, you can use the same macros. You can use the same mechanism that you use, start item, what have you. Or it's worth mentioning that every UVM sequencer in the test bench, each time a phase is entered, each time we begin a phase, it queries the configuration database for a default sequence. And then it builds and starts that sequence. Here, this test says that when the bus sequencer enters the configure phase, it should run the register configuration sequence. Which mechanism you use depends on various factors, and you get to decide. When we're generating stimulus, we often want to send all our stimulus before the test finishes. We want to somehow tell the test, we want to object to the end of the test, even the end of the phase. We want to object to the end of the phase until that body method has finished running. So you have to do one of two things. You have to manually manage the objections, or you have to build sequences that manage the objections themselves. You saw an example in John's. You could simply just create the sequence, grab the phase handle, and raise an objection, do whatever you want, Start the sequence, wait for it to finish, and then lower the objection. If you want to build sequences that manage objections themselves, so when I start the sequence will object until it's finished, then if you look in the UVM user's guide, you'll see code very much like this that says, okay, when the start method of a sequence is called, the first thing it does is call a pre-start method. So I can build a pre-start method, a callback method, that basically looks to see, do I have a phase handle to actually object to or not? Did somebody tell me what my phase is that I start within? And am I the parent sequence? If I'm not a parent sequence, I'm going to assume that my parent is managing objections or somebody else is managing objections. So anyway, there's some fiddling about you have to do if you want your sequences to raise objections. When Uwe talks, he's going to talk about how this code is done differently in UVM. This is the way we've done it. This is what the UVM User's Guide in 1.1 talks about doing that. But Uwe is going to talk about how we can get rid of that in UVM 1.2. So what is a UVM test? Well, as John mentioned, the UVM test is really something small. It's not your entire test bench. It's really just, I want to talk about tweaks and changes that I need to make to this existing large verification environment. There's one of them per simulation, and it's the top. It's the uppermost level of the component hierarchy. And typically, we will extend the UVM test class to create a base test that will itself build that environment. So the top here will build my test bench environment. And then I will extend, or my test writers will extend this base test to add those little tweaks and changes everywhere to create the stimulus and to create the test they want to build. An example UVM test, like a more real one, here I have a long test. I want to generate a lot of traffic. So I'm going to extend from my base test. It's a component, so I'm going to register it with the factory in the first method. And then in the build phase, I'll do things like, and I think John mentioned some of this sort of thing, I can set a type override. When anybody asks for a bus transaction, give them a big bus transaction. What is a big bus transaction? Well, presumably it's subclass bus transaction and added some constraints to say, look, the length is always 255 or something like that. I've added more constraints. I take bus transaction, I subclass it, and then I tell everybody to use it in this test without touching the code of bus transaction, without touching the drivers and all the other elements of the test bench. Magically, all my transactions become big. I could do this other ways as well, but here I say, look, this sequencer, I want it to run the bus basic sequence. My test should call out what sequences run. I could, in the main phase, simply raise an objection, build and run the sequence, and then lower the objection. But you're kind of constrained in these slides. And then I can do something like, I can tweak the knobs of my sequence in my test. I can tell it any sequence that runs on the bus sequencer that has a sequence length parameter, give it 1,000. So when my sequences that run on that sequencer ask for a sequence length, they get the number 1,000 from the config database. So in this way, I can radically change the kind of behavior that my verification environment generates in only a few lines of code, without touching it, without breaking it. I can change the kinds of transactions, I can choose the different sequences that run, and I can change the kind of behavior that we see the sequences generate. What else does the UVM test do? Typically, my verification environment will need handles to the pins that the components are using, so I'll put things in the config database, then I'll call the UVM package's run test method. This global method is called run test. Run test will build the test and then start phasing that test. So that component, that UVM test, its build method is called, as we saw in the base test. It'll build the environment. The environment's build method is called to build the agents, and on down the line. Which test is actually called? Well, we supply a runtime plus arg to the simulation to tell it, I want to run the bus long test, or I want to run another test. And typically we'll run lots of these in parallel, thousands, with different seeds and what have you. So the run test method queries the command line. What test am I going to build? And then that's how it knows which one to build.
We're going to talk about the register layer now. The whole thing about the register layer in UVM is it adds another layer of abstraction and therefore improves reuse. So the whole idea is as John and Shawn talked about, we have the sequencer here that is running sequences generating bus-specific transactions to a given address with a given data, and then that goes to the driver and onto the DUT. What we really want is to be able to take that up a step higher so that we can think about things in the way that we actually interact with the device. So we think about it in terms of the actual registers that are in the device. We don't really care how that information gets into the device. So by bringing it up another layer, we can think about things in terms of those registers that are in the device. So we can say write to the config register with a given data rather than having to worry about the address. So if we change the implementation of our DUT and move the configuration address around, great. So we can move the register in the DUT, and we don't have to change the sequences that we're generating at the register layer because we're still writing to that same register. It just happens to be at a different address. So we have a number of use models that we can use registers for. The first and most obvious is stimulus generation, right? So we're taking this stimulus one level higher. As we talked about, we can talk to a given register rather than having to worry about the address. This improves reuse, so we can actually reuse these register sequences as we go from one protocol to another. The device still has the same set of registers. The way the information gets into the device is specific to that given protocol, but the register itself doesn't change. We can also access it through the front door and the back door. So the front door, we actually go through the agent and onto the bus. It actually takes time. The back door is sort of a shortcut. It allows us to go directly into the registers to set things up without having to waste simulation time. The other thing we can do is deal with this in terms of configuration. And this takes it to another layer of abstraction, if you will. So perhaps you have a device that you want to set some piece of information about it. In order to do that, you need to execute multiple writes. You have to set several registers in order to get this thing into a particular mode. So in the same way that we can create a sequence at the bus layer that does several sets of transactions, we can do the same sort of thing here. We can create a configuration sequence at the register level that sets those registers to a given device. So we can say set the baud rate to whatever, and then that can actually make several different register accesses happen to get your device into that particular configuration. And the other thing that we use it for is what we call analysis mirroring. So what we're doing with the register layer is in our test bench, we are creating models that represent the contents of the registers in our design. And so by keeping track of what we think those values ought to be in the test bench, we can check them so that when we actually go and access the physical registers in the DUT, we can make sure that they're correct. The way that we present this information to you is we have a set of registers. The register is made up of a set of fields, and those fields can be one or more bits wide, but we deal with them in terms of fields. So there's this notion of a field in UVM. And then for each of those registers, we create what we call a register block. So that contains all of the individual registers and all the memories. And this is what corresponds to the registers in your actual block. Right? So you have a set of registers in your device, and you have a set of registers in your register block in your test bench. The other thing that we then have to do is take the registers in the register block in our test bench and map them to those physical registers in our device. And we do that through what we call an address map. And so for each interface into the DUT, we have a separate address map in the register block that we use to access those registers. There's a default address map that we use, or if we want to go through the other one, we can specify that explicitly. So there's one map per interface. And then in the same way that you might have hierarchical blocks in your DUT, you can have hierarchical blocks in your test bench, so the register blocks themselves are hierarchical. So you can have blocks made up of other blocks and additional registers, etc. So that's how we keep track of the information in the test bench and map it to what's going on in the hardware. So in order to do this, we have to write some code to set things up. So here we have our CSR register. It is extended from the UVM reg base type. And it is a UVM object, so we use the UVM object utils to register it with the factory. So all these things are just the same as any other thing in UVM. They're registered with the factory, and we can override them if we want. So what we do is we specify the fields in that UVM reg. So each of these things is a UVM reg field object, and we can randomize them. So for all of the different fields in there, we can specify them. So if we wanted to randomize this register, we could do that, and we can set constraints on the fields and whatever we want to do there. Then in the constructor, we give it a name, and then what we do inside the constructor is we call super.new, which actually calls the constructor of the reg base type, and we specify in that constructor some specific information. So this goes beyond just the name for an object in UVM, and we specify the width, whether we're going to have coverage with it. So there are specific coverage metrics we can set for the register as we create it. And then we have a build method. Notice this says build, it does not say build phase. So I suppose on behalf of the committee I should apologize for this, but this is how we do it. So there's a build method for the register, and inside of there we go and we create each of the fields. So the UVM reg field is a UVM type, and we use the type ID : create, as John says, to specify each of those fields. And then once we've created the field, we go and configure the field. So each field has specific information associated with it. So we have a size. So this is the parent, so we know that it's part of this register. So we have the size, the least significant bit, the access mode, the volatility means whether or not it's going to get kept. Usually that just stays 0, the reset value, and then a few other things. So these are the key pieces of information that you want to set. So for every register, you have a reset value that you set for it, whether it's read, write, etc. So now we have the ability to go and access this register and deal with it. So we can do things like we can reset it. We can go and look at specific fields of it. We know how we're going to access it, what the most significant bit is, etc., and then we can read it and write it. Okay, so that's the register. Then we want to take that register and put it in a block. So we have the address map that points to those registers, and in that block, we're going to specify all of the registers and any subblocks that we might have. So inside of this register block here, we declare all of the registers that are part of the register block, and we specify the address map that we're going to use. So we're going to have to deal with that address map in a minute. And then we have the constructor for the register block itself. And again, we can specify coverage for that register block. So this actually sets coverage for all of the things that we haven't set explicit coverage for when we declared the register. Then in the build method of the register block, and again, this is build, not build phase, what we're going to do is we're going to create each of the registers, call configure on it, and call build on it. So for every register, we're going to do each of these 3 steps. We create the register, we configure it, and we build it. So that's going to call the build method that we defined for the register itself, so we can make sure that it has everything that we need. And then we specify the HDL path slice here. What this says is when we go and access this thing in the hardware, this particular register is going to be called CSR, and it's going to go from 0 to 7. So as we'll see, when we go through the back door, we actually have to be able to reference that piece of stuff in the actual RTL by building a path of concatenating strings, and the leaf node of that string is CSR, which is that specific register. So that's what the HDL path slice is. We can also add another HDL path slice for the gate representation of the device if we wanted to. So we have a different name for that. It's also 0 to 7. And then we go and create the address map. So this is our APB map. We have the base address, the byte width, and whether it's little endian or big endian. And then we tell it to add the CSR register to that address map at this address, and then it's read-write. So for every register in the block, we build the register, we specify the path slice for it, and then we add it to the address map. So now the address map knows all of the addresses of all the registers that we're going to use to access our block. Then we have to specify the HDL path for all of the registers that are specified in this block. So top.dut for the RTL, that means that our RTL register is going to be top.dut.csr, and it's going to be 7 bits wide, starting at 0, the least significant bit. So that's our CSR. And in the gate level representation, it's called CSR DFF. Now at the gate level, it's top.board.dut. So we have a different path to the top of our device hierarchy, but the register is still called CSR. And then the last thing we have to do, most importantly, is we have to call this thing called lock model. How many of you have registers in your actual physical hardware that spontaneously move around? I didn't think so. So we call lock model to make sure that you don't do anything stupid. Then we also have this notion of hierarchy in register blocks, because as we said, you may have an RTL block with registers in it, and that may be part of a bigger RTL block with other registers in it. So we have multiple register blocks here, SPI registers and wishbone registers. So our SOC block here is extended from the reg block, registered with the factory. We have the constructor for it. So we also have a build method for this now, and we specify the default map. So we're going to create a map starting at base address 0. It's little endian. And then we specify the SPI register. So this is the SPI reg block here. We're going to create it, configure it, and build it. So for every block in our hierarchical block, we call configure and build the same way that in any block we call configure and build for the registers. So it's just all hierarchical, so we're doing the same kinds of things. And then we add a submap here for the default map of our SOC block, and we're going to use the default map of the SPI reg for that, and we're going to use the default map of the wishbone reg for those. So the SPI reg starts at 0, and the wishbone reg starts at 1000. All right, so now we have our hierarchical block where everything in our register block here eventually maps down into an actual physical register somewhere in our RTL. I don't show here, we also have the HDL paths for this, so it just builds it up as you go. In the register map, we have offsets for the registers and the memories. The register map itself has a base address, and then we calculate everything off of that, and it can be hierarchical, it can have submaps, etc. But it also provides the means to actually access those registers. So it's not just address information, it's some other stuff. So we have a handle target sequencer. From the address map, in addition to knowing the addresses that we're going to deal with on the bus, we also have the sequencer that is going to go through the driver to that bus. So we have a pointer to the sequencer, and we also have this thing called a register layer adapter. Again, we're specifying things in the register layer at this higher level of abstraction, but we need to be able to go down to the actual physical bus transaction, so we need a converter to do that. And that's what the adapter is, and so we specify that. Again, a block can have more than one map, and so each of those maps has its own sequencer and its own adapter, given whatever the ultimate bus transaction is going to be for that particular address map. When we set up the register map in our environment, in our build phase method, because now we're in a component here, so in the build phase method, we are going to configure that environment. So in the environment, we're going to go to the configuration database and pull out our environment config object and set it to mconfig. And if there's nothing there, we set an error, right? So this is just good coding practice, covering your bases. So if you're looking for something from the configuration database and it's not there, you should specify an error. Then in the connect phase method, this is where we're going to actually set all this stuff up. So we go and we look at the mconfig object that we just got out of the database. So this is all the environment configuration information that the environment needs. And we go and look and we say, is the agent active? And if it is, that means this agent is actually going to be driving stuff there. So therefore, we need a converter to go from the register layer to the APB layer. So we're going to create an adapter of that type, and we'll see in a minute what that adapter looks like. Then we go and we look and we say, are we the parent? So if getParent returns a null, that means we're the top level thing, so we're the ones that have to be responsible for dealing with this. So we call the setSequencer method of the address map in the register model that was passed in by the config, and we set that to be the sequencer in the APB agent. So we set that handle right there. Now our address map knows which sequencer we're actually going to be executing on. And then we set autopredict here to 0. So this is the default. This just says there's some built-in stuff in UVM that will check and make sure that the values that we get are the things that we expected. So we're just going to go ahead and use that. I didn't have enough time to go through all of the prediction methods. There's other information that you can go take a look at. So what happens when we go and access the registers? Well, when we do an explicit register access, we're going to call a method. So there's a generic register command. So we say register.read, register.write, and we pass in the data. So for each register, there's a read and a write method that is part of the UVM reg base class. That register transaction is then passed into the address map where the adapter converts it into a bus transaction. And then it gets sent through the sequencer to the driver to the DUT. And notice the monitor also detects that transaction going on there. And that'll be important in a minute. So what happens is the register sequence generates a register level transaction. It goes to the address map, gets converted into a bus transaction, and then sent down to the driver. So as far as the driver is concerned, it's just getting a bus level transaction from this sequencer. It doesn't know that that sequence actually pulled that transaction from the register layer. All it knows is it's getting a bus transaction. Then on the upstream side, if you will, so we have this thing called a predictor, and his job is to actually update the value of the register inside that register model, which is sort of the whole point here, right? We want to make sure that the value that we're tracking in our test bench matches what's going on in the DUT. So the bus transaction that the monitor saw gets sent to this thing called the predictor, and the predictor has a handle to that register converter, so it converts back the other way up to the register layer. So we check and see what that value actually was. So when we do a write transaction to the DUT, we just take that value as a given, says this is what the value ought to be, so we use that to update the model in the register layer. On a read, we get the read value back, and we say, oh, okay, I guess that's what the actual value is, so we go and use that to update it. And then that predictor sends that transaction out its analysis port. So what that means is up here, we have the rest of our verification environment that is dealing with transactions at the register layer. So if we have a scoreboard that is looking at what's going on inside of the device, that scoreboard is dependent on the implementation of the DUT, what those registers are, what they do, not where they happen to reside in the address space. That's the whole value of doing this. So we can think about interacting with our DUT and the behavior of our DUT in terms of the registers that we're going to use to interact with it, which is the way we want to think about it anyway. So when we go and actually access those registers, there are a number of things that we can specify, and we actually have a lot of options here, as you can see. The important ones are the status field, which comes back and tells us whether things actually worked. The data field, of course. There's also a path that we can use to specify whether we're going to go through the front door or the back door. And again, that is dependent on whether or not we want to actually simulate going across the bus or whether we just want to go directly in and muck with the data. There's a specific register map that we can use to access it. So normally we would access the default map for the block that the register resides in, but if we want to use a different map, we can do that. There's also a parent sequence that we can specify if we want. So if we're in a hierarchical specification, we can do that. There's a priority. There's a transfer extension object, which I've never used, so don't ask me about that. And then if we want to specify a file name and a line number for error reporting, we can do that as well. The good news is that most of these things have defaults. So a typical register access looks like this on the bottom here. So we have the register model dot register, the control register dot write. We pass in the status object so we can see what happened, the data that we're going to actually send, and the parent, which is this. Notice status and write and data are the first two fields. The parent field is a little bit further down. So if you only want to specify these three arguments, you can specify the first two by position, and then parent, you have to say dot parent. If you just say status wdata this, it will think that this is the path, and you'll get an error. So these are the only three that you really need to set, and this is what it looks like. So the only problem with this is that we keep having to refer to the register model and the control register and the write and the parent. So there's a lot of additional stuff in there that maybe we don't really want to do because we really want to just think about this in terms of dealing with the registers, right? Ideally, as I'm writing my register sequences, I don't really want to know that I have a register model in my test bench and that other things are going on. I just want to think about things in terms of those actual registers. Front door access methods, they consume time on the bus, and they look something like this that we just saw, right? So register model dot register dot reader write, and we specify the status, the data, the UVM front door is the path, as I said, UVM front door is the default, and then the parent. So if you want to explicitly say, I definitely want to do a front door access so that somebody looking at your code can actually know that, you can specify it this way. And what happens is we go and we do the transaction on the bus, and then we update these two values in the register model. So there's two values. One is called desired and one is called mirrored. Mirrored is the value that, as close as we configure, is what is represented in the hardware. So if you go and do a register transaction and then your hardware magically goes and mucks with the values in your register, unless you can detect that behavior from your test bench and update your register model accordingly, the things are going to be out of date. So the mirror is as close as we configure it, this is what we think the hardware actually is doing. And the desired value is, this is the value that we really want it to have. So we maintain both of those. Ideally, they should be the same all the time. But as we all know, it doesn't always work that way. So when we access the front door, we go and do the bus transaction, and then after that happened, we have all the information we need to go and update the desired and the mirrored values in the register model. However, we can use these methods called readReg and writeReg, and these are actually methods that we'll see that are part of the thing called a register sequence, and they automatically take care of, for you, the parent argument and the register name. Now what we're going to do is, so we say writeReg, readReg, we specify the register that we're going to use as a subset of the register model. We still have the status and the data and the path, but we no longer have to specify the parent because of the magic of the fact that we're in a register sequence here. So it does exactly the same behavior on the bus and in the register model, but it's a slightly more direct way of specifying it at the transaction level. In front door accesses, you can access individual fields as long as your hardware supports it, because what you're going to wind up doing is doing actual bus transactions in your system. So if your hardware lets you muck with just a piece of the register model will reflect that as well. Right? So whether you have a byte lane or whatever. For backdoor accesses, looks exactly the same except we specify UVM backdoor. And what happens here is we actually go around the driver and we go directly into the register. So again, we're not simulating any time on the bus. All we're doing is going around using VPI or whatever mechanism your simulator decides to use to go and actually set those values. But again, the desired and the mirrored values get updated at the end of the transaction. So as far as the register model is concerned, the only difference between a front door access and a back door access is the amount of time that actually occurs on the bus. So we're still keeping the desired and the mirrored values in sync as we go and muck with the values. However, when you're doing the backdoor access, because you don't have the ability for the hardware to go and muck with the values based on byte lanes and other things, you can only access the full register value through the backdoor. If you want to change just a field, you can do a read, modify, write through the backdoor, and that's the way we would recommend doing that. There's another backdoor access method called peek and poke. So it looks pretty much the same. Specify the register through the register model, the status, and the data. Again, these consume no time on the bus. So poke actually goes and sets the actual value, and peek will return the actual value. But they work on fields, but they actually don't do anything to the desired or the mirrored values. It may be the case that you want to do a bunch of stuff through peeks and pokes and then do one access at the end to update the desired and the mirrored values or what have you, right? So these just allow you to go directly into the hardware and not have to worry about anything else. So since we're updating the actual value, it will go and update the mirrored value there, but we're not keeping track of the desired value with peek and poke. So we also have direct access modes here called set and get. And these access the desired value directly. So if you wanted to randomize your model, then you can call set and get in here. And then after you set the desired value directly with set or get returns it, then you can actually call update register, which will take that desired value and cause the transaction to happen to do the actual register. And you can specify that through the front door or the back door. So this says, okay, I want to make sure that the hardware is going to have the value that I think it should have in my register model. So I call set to set the desired value, and then that will cause an actual transaction to happen to update the actual value in the hardware. And then once we do that, we update the mirrored value. So update register will take the desired value, make it happen on the bus to set the actual value, and then reflect it in the mirrored value. What that means is doing a set plus an update is the same as doing a write or a poke, in that it causes everything to get updated. Then there's also the mirror method. You call mirror register, and again, you give it the register through the register model, the status, and then this next argument says UVM check. So you can actually tell it whether or not to do anything with the value there. So we're basically going to check that the mirrored value matches the desired value when we do that. So we can do it via the front door or the back door, and that will actually go and cause the value that's in the actual register to get reflected up into the mirrored value and check that against the desired value. So you have a number of permutations here that you can use depending on what you want to consider the known good value, what value you want to test against, whether you want to actually check it or just take the value as given, a number of things that you can do here. Let's take a look at the adapter class here. So again, this is something that is part of the address map, and it allows us to convert from the register layer to the bus layer. We have one argument here on the reg to bus. It is the register transaction, in this case, reg bus op, RW here. So what we do is we create an object of the return type, the thing that the bus transaction that we're going to use here, in this case, AHB sequence item. And we take the fields from the register transaction, we look and see whether it's a read or a write, and we update the values of the bus transaction based on the values that we got from the register. So the register transaction really just has address, read, write, and data. It's a pretty generic transaction. There might be some other fields in there, like width and stuff like that, but we just take that appropriate information and use that to shape the transaction that's actually going to go across the bus. The reg bus op here, this is a struct. It's not an actual transaction, because all this has is, as I said, the address, the data, and a little bit more information in there. So we just take those fields out from the register, right? The register transaction itself is an object, but all the information that it uses is this struct that we deal with. So we go and we create the bus transaction. On the other side, on the bus to reg, so we're going from the sequence item type, the bus item, up to this reg bus up struct here. So we're going to convert from the bus back up to the transaction. We basically just do the reverse here. So we look at the sequence item, we do a cast just to make sure that it's of the appropriate type, and then we take the values and we update the value in the RW argument, which is a ref, which gets passed back out. So there's no return statement on the bus to reg call. Basically what we do is we have a limited number of fields in our register transaction, address, data, etc. We take those, we use those to fill in the bus transaction, and then on the reverse, we take the bus transaction, we look at those fields in it, and use those to update the register transaction. Pretty straightforward. Same sort of thing you would do similar to if you're going between system Verilog and system C using something like UVM Connect. You basically take the fields, pass them over, update the new object, and you're off and running. One thing about it in the status field here, you can specify UVM is okay, UVM not okay, and you can also specify UVM has X. So if the value that you get had an X in it, it may be okay, but you want to know about that. So these are the status values that you're going to look at when the register transaction gets finished, and you can operate on it appropriately. Now we're going to go and integrate our register model inside of our test bench. So we have our environment in here. In the environment, we have our configuration object that we talked about, and we have a register adapter that we're going to have to create here, and a register predictor. So this is sort of the register layer monitor, if you will, right, that we saw in the previous slide. We're going to declare these things and then assume that we've just created them in the build phase as we normally do. But in the connect phase here for our environment, we're going to look at this and make sure that there's a register model in the config object, because we got to have one because we're dealing with registers. Assuming that we have that, we're going to create the register adapter, and then we're going to set the sequencer in the address map of the register block as we just saw there. So this is our agent sequencer. And we specify the converter here, so reg to APB. And we're doing this in the connect phase, by the way, because these things aren't really components. We could actually do the create in the build phase of the environment and then do the connections here, passing in the set sequencer. But I actually prefer doing it all together here because it actually is somewhat based on the information that we're going to get when we look at the config. So rather than having to go look twice, we can just look once and go and build it from there. So we set our sequencer, we set our predictor. The map for the predictor is going to be the one that was passed in through the register model in the config. So the predictor needs to know what that address map is because it has to go refer back to it to get access to the converter and to know the addresses. So we integrate that there. We also set the adapter in the predictor as well. So that's the reg to APB. So everything there is done in the connect phase. And then we actually do the connection. So the register predictor gets connected to the analysis port of the APB agent. So the monitor's analysis port goes out the agent, goes to the predictor's input, and then the predictor has all the information about how to go back up to the address map and make that all happen. We said before we want to deal with these things at the register layer as a sequence. So we have this thing called the UVM register sequence. It is extended from a base class of UVM sequence parameterized by a UVM reg item. So it's sort of parameterized by a parameterized type. This is all fine here, don't worry about it, because when we go and extend the UVM reg sequence, we're going to tell it what type of bus transaction we're going to use. And there's this thing called model in the register sequence that is the reg block. So we build into the base class this idea that there has to be a register model that we're going to deal with. And then we're going to extend that register sequence, and we set model to be of the correct type. In the base class, it is just of UVM reg block, but we're going to override it to be a reg block of the appropriate type that we want to deal with. We call the constructor, and then there's a body method here that we're going to set. This is where we actually go and interact with the registers in the device. So we call write reg, read reg, etc. So write reg and read reg are actually methods of the register sequence base class, and they know that we're using a model here, so that's how we get around that. So write reg, read reg are methods of the register sequence, and they allow us to interact directly with those models. So we have these convenience methods to go and write the registers and the memories. Then what we do is we extend that to be our specific SPI bus-based sequence here. So we're extending that reg sequence even further now, and this is the model for the thing that we're going to use for this particular application. So we have an SPI register model type, we have a config object, and then we're going to have the ability to randomize the register data and return the status. So this is what our register stimulus base class looks like. And then in the body method, we're going to use the config database to get the environment configuration so we can figure out what's going to happen here. What we're doing here is the config object that we pass into the environment is the same one we're going to get from our register sequence because it has all the information that we need. So rather than having the environment pull that information out and send it into the sequence, which we could do, we know that we're actually going to go and look for an environment config if we want, so we can do it that way as well. That's completely up to you how you want to handle that. But the point is that the register sequence needs to be able to get from the configuration database what it's ultimately going to use to know where the register model is. Wherever we get that from, we wind up setting that to the model pointer, and that's the thing that everything's going to use from there on out in the write-reg and the read-reg methods. So when we start at the top, we have our register model, and that gets passed through the config database to the environment, and then from there down into the sequence and everything else that needs access to the register model. Then we're going to extend that base type, and this is where we're actually going to go and create some specific stimulus here. So we have here a constraint for divider values, so it's an array that we're constraining here. And what we're going to do is, because we've specified the given fields in here, we're going to randomize this transaction. So the data value will get randomized to be one of these values. I didn't actually show the declaration of data there. So we randomize it. You can think of these as values of configuration information or whatever that we're going to send down to the DUT. So we're going to randomize this particular transaction and call write-reg to the divider register with one of these values, and that's going to randomly set our clock divider or whatever it may happen to be. And then we go and make sure that that transaction actually worked. So we make sure that status is okay. So we write the value. We may also decide we want to do some looking, so we're going to further extend that to a different data sequence now. So in here we have an array of data registers, and those are going to be set to these specific registers from our register model. So reg 0, 1, 2, and 3. Then we can shuffle the order of that array. This is going to make sure that we don't have any data dependencies as we update these register values, right? So you can randomize the order that we're actually going to do the writes in. And then for each element in that array, we are going to randomize the value, and then we're going to call update register through the front door. So we're actually going to make a transaction occur to update the register in the device based on that value. So whether we do update or write, read, whatever. Now that we understand how to do that, and I realize we went through that fairly quickly, let's just suppose that we start with a block level thing down here. We have an APB interface on one side of our SPI master. So we have our register sequence here, and we have an APB bus agent here. So we're going to create transactions for our APB bus and go through the agent and get over to the master here. So this is our DUT down here. Let's suppose that we take that block now and we put it in a system. And so now what we have is, as part of the system, there's some sort of a bridge here, right? So instead of being an APB interface to the DUT, we now have an AHB interface. The sequence up here, because it's based only on the registers that are in the device, doesn't have to change, because the fact that the address of this block and the protocol that we're using to communicate with it has changed is irrelevant to the fact that we're still accessing those same physical registers in that particular block. So this is where the value of the register layer is. It moves you up that one level of abstraction and gives you an additional degree of freedom in here as you go and make changes, whether you go from block to system or if you go from project to project, if you're going to reuse this particular block in a different system with a different protocol or different bridge or whatever, the way that you're going to access those physical registers still stays the same, and the register level sequence allows you to deal with it in terms of those registers. Summarizing, the register model follows the hardware structure, right? We have fields, we have registers, we have blocks, we have maps. We can access the internals of that register model through the get and the set to update the desired value. And we can also access the actual physical registers in the device through the front and the back door. The access is layered through the register model, so we have these generic sequences in terms of the registers that get targeted to specific bus sequences, and therefore the reuse of those sequences is pretty straightforward. And we recommend that you use the convenience API in the register sequence, so you're using write-reg and read-reg instead of write and read. It makes things easier to just think about at the highest level of abstraction, you're dealing with the registers. You don't want to have to worry about which register model you're using and all that kind of stuff. You just think of it in that way. And you don't have to worry about the parent argument. And so the other thing that we provide, which I haven't shown here, is when you create all of these registers, there are built-in sequences for sanity testing. So you can actually go and for every register in your block, there's a sequence that will go through every register in the block and read the value of it to make sure that it corresponds to the reset value, for example. So you can do things like walking ones to all your registers, make sure that for all of the read-write access ones, you can write them and then read them back, all those kinds of things. So those are there as well. That's pretty much everything that you need to access your device in terms of registers.
My name is Uwe Simm, and I want to bring you something about what is the news about UVM 1.2. This is something for people using UVM 1.1 on a regular basis. First of all, let's talk a little bit about UVM 1.2 in numbers. UVM 1.2 is about 90 mantis items. 90 mantis items means 90 different things being addressed. That means about 60 bugs and clarifications have been changed. So code in 1.1 has been bug fixed, and that's in 1.1 in 1.2. And we also added about 30 enhancements. Enhancements, they go from single line enhancements to bigger enhancements. So these are changes to the add-ons to the existing functionality in UVM 1.1. If you look at the core code, we're talking in terms of UVM source code, we're talking about of 65K lines. That is almost equally split between documentation and code itself. We consider the documentation also as something we deliver because the documentation makes up the HTML documentation. So we're not just coding, we're also putting the documentation in so that you can use really the code itself. And UVM 1.1d had about 56K lines of code, so that makes a kind of an increment of 10 to 15%. If you look at Git, the Git is open and on SourceForge, every one of you could look at the changes. It's about 12K lines of code added and some K lines removed, so it's a kind of 8K lines of code has been added. As I said before, it's about 10 to 15% more code. And we also not just added code in the core itself, we also added developer tests. The developer tests are typically the tests you do not see, but they are important for the developer code base because they're exercising each of the features in more detail than what you will do. So what can you really expect from UVM 1.2? First of all, you can expect bug fixes. I already mentioned that. You can also expect performance fixes. We put a lot of fixes in which address performance degradations. So you run and certain things didn't happen really in time. So we put a lot of fixes in. We put a lot of cleanups in. There has been a lot of bad code in there, and really this old code got cleaned up. There are now much better implementations in various places. There are enhancements, I already said that, and a reminder of the presentations, we'll talk about these enhancements. We will see, of course, there are API and semantic changes. So in UVM 1.1a, 1.1b, 1.1c, 1.1d, we try to retain the same API. We didn't change the API, we didn't change the semantic, and it was really a critical bug fix. So they are compatible. If we move to UVM 1.2, most likely that isn't true. So there are changes in the API. If it affects you or not, different story. We also, for UVM 1.2, we changed and updated the UVM user guide. This has been cleaned up. A lot of the old stuff, which basically inherits from OVM, has been removed, cleaned up, and all the use models have been properly documented. In summary, what you get in UVM 1.2 is mostly compatible UVM version, compatible to UVM 1.1. However, for your project, it might not be 100% code compatible. I would expect a few small changes in order to get your UVM 1.1 code running on UVM 1.2. No major changes, small changes, but they are. And another word of caution. The following slides, they show a lot of advanced stuff. They show a lot of corner case things, what we added, what we enhanced. Not everything is intended that you need all and everything tomorrow in your own test bench. Use it wisely, talk to your vendors, talk to the other people. If a feature for you really makes sense, if you really need that or not, use it wisely. So, most notable change in UVM 1.2 is reporting, and a big part of the reporting infrastructure has been changed. Reporting infrastructure typically means that's the infrastructure inside the UVM core. For the end user, not much has changed. The reporting API has become object-based. In the past, if you extended report server and so on, you had a lot of arguments in there. All of that has been collapsed. There are now message objects, and they are being passed through the APIs, and they simplify the whole handling of things. You also have now the ability to add values and objects to messages. You can record messages, and if I talk about messages, it's not the normal transaction recording. I'm talking about the messages, tick UVM info, UVM warning. You can record these messages to a storage, to a text file, to a vendor storage, to a transaction database where you can browse these messages, not just in the log file, but you can push these messages in a dedicated database. All UVM core messages are now routed through UVM messaging. No messages inside the UVM core are emitted via $display, $write, or something like this. That means you can affect all and every message with the UVM message controls. Push them into a file, change severity, filter, and all of that. Catch messages. All of that is now being routed. The effect of that is that, unfortunately, since it changes the output format in some places, some of your, eventually if you're using code files, that might change between 1.1 and 1.2. And there's a new add-on, message macros, UVM info begin, UVM info end, UVM warning begin, and so on. And you can use these macros like normal messaging macros, but you can add additional data into these messages. I have a small example here. First of all, we construct an instance of a message object, and then we start a new message with all what we had before, like a tag, a message body, and a severity. That's the message object. And then we add objects, data, into that message. This data is printed or recorded along with the message. And it's better because in the past you had to flatten all of that information into the message string. That's not necessary anymore. You put it in the message elements. You can construct database, basically a backend where the data is going to. You create a stream. It's basically the logical stream inside the database. And then you can record the message, or you just process the message itself. Basically, that would expand the message, go through all the filtering, and then would emit the message. Changes in sequences. In one of the previous presentations, we saw this raising and dropping of objections. And we did an extension in the sequences that if you use the set automatic phase objection, this allows the UVM library to raise and drop objections automatically. So you are not required to do a phase.raise objection, phase.drop objection anymore. You set that set automatic phase objection once, and then starting a sequence raises the objection, ending the sequence drops the objection. So you're relieved from all this phase.raise and drop. Some people like the raise and drop, some people don't. That's what you can use in that scenario. Also, you can control the sequence for a phase now via command line argument. So you can supply plus UVM set default sequence. You have to supply a sequencer, you have to supply a phase, and you have to supply a sequence type. And that allows you to control the sequence which the sequencer starts in a particular phase directly from the command line. And the last thing we saw it also in some slides, you know this magic variable called a starting phase. In the past it was a kind of a magic variable which was sometimes set, sometimes it was not set. Since it's a variable, it could change over time. And if you're raising and dropping objections then on something which you do not know what it is, you could run into very difficult and problematic scenarios. Therefore, starting phase has been wrapped, has been guarded, so that you are required now to do a get starting phase and a set starting phase. And it's guarded, so once you read it, you cannot set it anymore. And this basically ensures that starting phase is not changing for you. So the code today, if you're using starting phase, would look like UVM phase get starting phase, phase.raise objection, you do your UVM do's, and then you drop the objection. It's the same thing as starting phase.raise objection and for starting phase.drop objection. Point is, starting phase as a variable is not accessible, and therefore you have to go through proper accessors, and that ensures you're safe in terms of raising and dropping of objections. You're not dropping on and raising on something which isn't really relevant anymore. Registers. The most notable change here is VHDL backdoor support. You can now not just talk to Verilog, system Verilog registers via VPI. We also added VHDL backdoor support, which means VHPI support, so you can read-write through the backdoor into VHDL. And also an enhancement is that we are now able to control transaction order, especially if you have big registers and the bus width is much smaller. Think of it, you got a 64-bit register, you got only an 8-bit bus. That means if you want to transfer the 64-bit, you have to access that bus 8 times. It could be important in which order you read and in which order you write, because this could determine when value really takes effect. You're starting with the lowest byte or you start with the highest byte. So you now have a chance to control the order of which the sub-transactions go on the bus. A very small example here, it's a high address first policy, which has only a single method, it's the order policy. You get a queue of transactions, you order the queue of transactions regarding your needs. This is basically the highest address goes first. You make an instance of that policy, and for your register map, you set that ordering policy. And that would order all the accesses according highest address to lowest address. Objects. The most important change probably you already seen. I think there's already in the header, when you start up UVM 1.1, it's already showing that as a change for the future. UVM objects do require a constructor now. So you cannot go with the default constructor anymore. It requires a written constructor unless you set that define UVM object do not need constructor. So it's a default in UVM 1.2 that we require that thing. How does the constructor look like? Function new, string with a default argument, super new, and end function. If you don't like to write it, there's a script in the utils bins area. Just run it, and that script basically adds the 3 lines of code to the classes which do not have that constructor. It's a one-time change, not big in functionality. It solves some problems in the register area. Keep in mind, if you have UVM objects, add that constructor. Component names are now being checked for compliance. The main reason for that is that there are a couple of scenarios where you could, for an object name, supply something which is neither readable nor something which prints nicely or which has a lot of characters in there which makes it undistinguishable from other hierarchical things. For instance, if you have white spaces in there and if you print that, you won't see the difference between an object with a white space in its name and not with a white space in its name, if it's in the end or in the beginning. Or if you have a lot of dots in there. If you have a name A.B.C, if you print that, you won't see where the hierarchical delimiter is. So all of that is now leading to warning. You shouldn't be using that stuff. So far, it was only a recommendation how names should be constructed. This is now being checked. It's not enforced, but it's being checked. However, you're even allowed to make company rules and constrain it further. If you have your own rules, how names should be constructed, you can do that. You can enforce it. We also added a new type, UVM integral T, which is a 64-bit packed logic. And this is also supported in the APIs, most notably in the pack field int. Reason for that is you probably know all integral types are being modeled as UVM bitstream T. A UVM bitstream T is 4K of memory. So if you store a single bit via setconfig, you're not just getting a single bit, you're getting a single entry of UVM bitstream T, which is 4K. So it's quite big. In addition, all the APIs which are using UVM bitstream T are moving 4K in its arguments around. So if you can guarantee you're not exceeding the 64-bit, you can use the integral part, because it just typically fits in a CPU register and should be much faster in moving it around. Phasing. We removed objections for non-task imps. What does it mean? If you envision the whole phasing tree, the phasing nodes, the phasing imps, all the different things, it was possible to raise objections in any place. You could raise an objection to build phase, which is a function phase. You cannot object a function. It doesn't make any sense. You can also not object anything which is executing. It only makes sense to really object to the phase imps itself. So all of that is gone. If you try to do that, it now leads to an error. And it gives you an indication that the code you had in the past was actually not performing. That is gone. The code is now not letting you raising and dropping objections, something which isn't really used. There's a shortcut for getting the objection count, which is now the UVM phase.getObjectionCount. You can retrieve the number of pending objections for a phase. This is just a shortcut for getting the objection and then calling getObjectionTotal on that thing. So very simple convenience. A bigger extension is the addition of phase transition callbacks. You can now have a callback on any phase transitions. So whenever there's a phase transition from phase A to phase B, you're getting a notification. You can write your callback, instantiate that callback, and register with the appropriate phase. Very short example. This is the method, the callback method, phase state change. It gets the phase and the state change. Just printing it here. And what you have to do is you have to attach it to a phase instance and supply the instance of the callback. And that would, if you attach it to all and everything, it would give you basically a message that you're moving through the phases. UVM config DB. Meta characters and regular expressions in field names are disabled. Using that would lead to semantic issues, to performance issues. That is not going to work anymore. So if you do a set with a wildcard, sets with wildcards or regular expressions, this is leading to a warning. They are not executed. These field names are taken literally. So this field name is a /myComplexInt.star. It is not a regular expression anymore. This only affects field names, not scope names. Setconfig and getconfig in are deprecated. So if you use that stuff, you should either move or you need to enable the backward compatibility mode. The conversion script from 1.1 to 1.2 is trying to change that. UVM setconfig int to UVM config object or config int. There's one complication with the object here because there's a clone argument. The semantic is slightly different between the two. There's a mantis, read the mantis, and it's there. The script annotates the appropriate lines with that mantis, read it, and change it accordingly. Factory. The global variable UVM PKG factory has been removed. You retrieve the factory via UVM factory : get. You can undo a factory override that was not possible today by setting an override with the type itself. And as an advanced use model, you can replace the factory in order to trace or log calls or record calls or filter calls to the factory. So you could make a new factory which is just printing that a particular factory call has been executed and that it's just calling the original factory. This allows you to go in between the factory and the real factory instance, or to supply an own factory. Objections. There's only one big change here. It's a propagation model. In the past, we had this propagation model that whenever you raise and drop an objection, it would go to the parent, and then raise and drop in the parent would go to the grandparent, and so on. So if you have a lot of high frequency raise and drops, all your test bench would be doing is raise, drop, raise, drop, raise, drop, kind of on a cycle basis. And this has been changed. If you go to mode equals 0, means you're going to non-hierarchical objection. That means instead of going through the hierarchy, you're just raising and dropping objections in the root parent. That's much faster. And especially if you're having high frequency scenarios, it will show that. Okay, some miscellaneous stuff. We added data access policy objects called DAP, which give you basically a controlled access to objects. They are object wrappers. You can do things like get to log, set before get, and so on. They are general purpose access mechanisms. You can use them as a general pattern we provide. We added a visitor pattern infrastructure, UVM visitor, the visitor adapter, and so on. This is a general programming pattern. We use it in one place right now in UVM, but you may use it. I think it's a good pattern to use, and it has been added. UVM core service has been introduced. UVM core service is a common container for a lot of variables which so far were dangling around in the UVM PKG namespace. All of that moved into a container on its own, giving you the ability to override the getting of certain things, the setting of certain things, the overriding of certain things. That is all now captured in UVM core service. You can think it's like a mini factory for core UVM components. UVM sequence library is now documented and part of UVM 1.2. That was code-wise part of the core since UVM 1.1, but the documentation therefore was not really part of the standard. Code was there, it's now there. UVM severity type was an integer. UVM severity is an enum. We had two things for the same thing. One is gone. UVM severity type is gone. It's now just UVM severity, which is the enum. Just for safety, it's cleaning this stuff out. There's an additional class called a UVM enum wrapper. Going from an enum to a string is pretty easy, right? You just call enum instance.name. Going the other way around takes a little bit more. Going from a string to an enum, this class will do that for you. And there's one semantic change here. The UVM field enums, they now scan string types in addition. In the past, they just scanned the enums and ints, and you now get strings in addition. So you can set enums from the command line as enums, as literals, not as numbers. Messages in DPIC are routed back to UVM message facilities. In the past, DPI failures, VPI failures, they just were printed in the simulation log, not as UVM messages. If you have filters on this, you wouldn't see that. All the messages are now routed back into UVM. Everything which goes wrong in DPI, UVM part, is routed back and appears as UVM messages. You may use that facility to inject your own things into the UVM messaging if you're coming from DPI. In a lot of places, we did a separation of classes into an abstract part and in a default implementation. For instance, UVM factory in the past has been split in two things, in an abstract API, which is still UVM factory, and a default implementation, which is UVM default factory. We also have UVM report server split into the abstract part and UVM default report server. The default is a default implementation. The strict API is the old UVM factory or UVM report server. So whenever you override the UVM report server yourself, you typically go now for the UVM default report server, which is providing the same functionality as the old UVM report server. There has been some cleanup with some scope variables. I already mentioned the factory. There are some missing prefixes in this UVM underscore was missing. This has been added so that all the UVM variables names, class names and so on are prefixed with UVM underscore. Now the important question is, if you want to move from UVM 1.1 to UVM 1.2, what do? First of all, there will be a changes document. Right now it's an Excel spreadsheet. We're currently adding that. Release notes will have all the information, which Mantis items have been addressed, which are affecting the API, and they are all listed. You can go to the Mantis database and look at that stuff. And there are basically 3 migration scripts. One is, I already mentioned that, add UVM object new, which is adding the 3 lines of the constructor. We have UVM 1.1 to UVM 1.2, which is attempting to bring UVM 1.1 to a UVM 1.2 code level. And we have the old one, it's OVM to UVM, which has been renamed. It's now basically going with the same pattern, OVM-to-UVM. It's the old, if you go from OVM to UVM 1.0.